Yo,
Uh,
what's up? What's up? I finished chemistry physics section bank 2 today. Um, Getting wrapped up on most of the AMC stuff. Like, I'm gonna try redoing some of section bank volume 1. Um, and also just gonna do some psych stuff as well from volume 2. But like, obviously, with you, I like going over Chem Phys and Biochem. But yeah, today just same old. Want to go over a couple things that I found trouble with.
yeah.
Um, yeah, and this is the first thing.
Okay. All right. An electrically isolated thin spherical shell of radius 3 centimeters is made of a metal of work function 5 eV. What's work function?
It's the minimum amount of energy required for something to emit an electron.
Okay. And when you say emit an electron, what do you mean?
Like, uh, like, um, release an electron.
Okay, yeah. So, um, okay. Photoelectric effect, right?
Yeah.
Okay. All right, what is the maximum number? Oh, there we go. Photoelectrons that the sphere can emit when exposed to a beam of photons of 7 eV each. Um, okay, so we know that photoelectrons are going to be ejected because this energy photon of the photon energy is larger than the work function. Okay. Now I guess it's a little, they're asking about the number of the electrons, which is kind of like the number, like related to intensity in a way. So let's see. Use this per that to get that as the volts. And I guess that's for each electron.
So I was completely clueless about like what that thing on the bottom was. Like, was it the area of the sphere? Like, I just was so confused. I don't know what that was. Like, why is there a pi?
Oh, okay, that helps. Um, yeah, I want I think it might be like to be per. Well, I mean, it says times 3 centimeters. I was gonna think that it was gonna. Oh, wait, hold on.
That's what I'm saying. Like, what if it's the area or something?
The surface area of this sphere.
So I'm thinking because it'd be 4 over 3 times pi times r squared, but like r squared is 3 squared, so then 3 squared over 3 is just 3, right?
What did you say first? You said 4 thirds pi r what?
Squared? Is that like the surface area?
Oh, okay, okay. I thought you were saying something about the uh volume
No.
because the 4 thirds would be in the volume, right?
Oh, then I have no idea how this is working then.
I don't know. So it's what you're saying. It was just the 4 thirds part, but that made me think that you were saying volume. But so I guess this is telling us that this is so we know an electron has a charge of 1.6 times 10 to the negative 19 coulombs, right?
Hmm.
And I think what they're trying to show us here is the amount of coulombs per like surface area of the sphere.
Amount of coulombs per surface area of the sphere. Oh, got you. Okay.
Yeah, because
Okay.
that's the thing that we're shooting photons at to get electrons out of. So, okay. Now, let's see. The number of photons. Okay, okay. So we're gonna do this. We're gonna do like one electron, either like, is equivalent to 1.6 times 10 to the negative 19 coulombs. We can do that. So now let's see. Oh, wait. Coulombs per, it's in centimeters. But I thought it was supposed to be area, which would have to be like square centimeters. And is this equal a voltage? A voltage, I guess. 6 centimeters. Let's see. Okay, so this many volts.
What's KeV?
Sorry, the kinetic energy of the electron.
Oh, okay. Yeah, yeah, yeah. Yeah, so that's like the farthest I got. Like I realized that okay, 7 minus 5, 2 EV is the kinetic energy. And then after that I was just lost.
Yeah, now this is throwing me off here because if this is in centimeters, it can't mean area. I know that this is supposed to be, so like what I'm trying to do here is I'm trying to take a value of the number of coulombs to figure out how many electrons are involved in that. Now I see coulombs per like distance to equal the voltage. And re so I guess this is for pi r. See something. The E naught value, um, 4 pi, something with E, and then R. It doesn't say R squared, it just says R. So, okay, so this is in volts. To go from so an electron volt is the voltage of one electron, which is um 4.8 E negative 8 volts. 2 electron volt for the kinetic energy of the electron, and each electron has a charge of the 1.6 times 10 to the negative 19 coulombs. And that's okay. I guess we actually might not even need to do the stuff in it, like deal with this if we deal with that. So, okay, I'm gonna do this. I'm gonna do like 1 electron, or rather. Oops. Okay, so voltage is in joules per coulomb. Joules per coulomb. If I multiply this by coulombs per moles of electron, and then multiply that by moles of electron over number of electrons, I think that'll work. Okay, so let's see. Okay. Yeah, what the hell?
Okay, I don't want to spend any much longer on this. Let's see
Yeah.
what they do.
N times E. N is, what is,
What? What is N?
okay, I'm gonna just screenshot this.
N? Like newtons?
Like, my guess is that it's gonna be the number of electrons, because,
No.
and then E would be the elect, so yeah, something like that. But yeah, I'm gonna, I screenshotted it, so I will look at it. Uh,
Okay.
yeah, these are
Yeah.
pretty tough. Like, am not used to seeing this stuff, but
Yeah.
no excuse.
Yep. Um. Yeah. Okay. All right. We can go with this. Um. So the application of biocatalysts for enantioselective conversions in organic synthesis is important for the stereochemistry used in drug design. An example, so enantioselective I highlighted because it's like selecting for an enantiomer, enantiomer, I mean, sorry.
Uh,
Okay.
yeah.
Application of biocatalysts for enantioselective conversions in organic synthesis is important for the stereochemistry used in drug design. An example of this biocatalysis is provided by the synthesis of R compound 1 and S compound 3 as shown in figure 1, where the enzyme Candida antarctica is utilized. Cal B is a monomeric protein with a conserved core structure with an H-stranded, mostly parallel, twisted beta sheet flanked by two alpha helices. Um, when I see monomeric, I think tertiary structure.
Mm-hmm. Because
Yeah,
can't have a quaternary. Good.
yeah. And then, I mean, beta sheet, alpha helices, they're secondary structure, but altogether it creates tertiary structure. The overall experiment consists of two separate steps, synthesis of Rag compound 3 and its kinetic resolution. So kinetic resolution, would that mean kinetic like product?
I think so.
Okay. So it's like the faster one. It's might be less stable, but it's created faster.
Yeah. It's apparently it's a means of differentiating two enantiomers in a racemic mixture. So it you can yeah. So one of them can be produced faster than the other. Yeah.
Okay. In the first step, Rac 1 compound was converted into Rac compound 3 by the addition of two equivalents of pyridine, so I know that's a base, and 1.5 equivalents of compound 2 at 298 K in diethyl ether, which is that's a nonpolar solvent. Just like things are going off in my head. After extraction with hydrochloric acid and saturated NaHCO3, um, the product was dried with this is bicarbonate.
Yeah.
Okay. Dried with anhydrous Mg2SO4 and the solvent was removed. Vacuum distillation was performed. Um, Now, what is vacuum distillation? When I was reading it, I was like, oh crap. Honestly, I forgot. Um, so it's another reason why I wanted to go over this with you. They're gonna ask a question about this. But yeah, highlighted that. In the second step, rock compound 3 and the phosphate buffer pH 7 were stirred at 298 K, followed by addition of CaLB. pH of the reaction mixture dropped initially. Whenever the pH dropped below 7, dilute NaOH was added, and the reaction was stopped when the pH remained stable. Mixture was extracted with diethyl ether, and the products were separated by column chromatography. Further analysis of the products found that both R compound 1 and S compound 3 were formed in high percent enantiomeric excess of greater than 93%.
Okay. So tell me. So you should know the differences between the separation techniques in. So like for instance, tell me about distillation.
So distillation takes it takes boiling points to advance and it's to its advantage, I guess. Like what I remember simple distillation is the difference between the two boiling points is less than 25 or no, bigger than 25, while fractional is difference is less than 25.
Uh, so that's the simple versus fractional. Um, but what about like regular distillation versus vacuum distillation? The thing is that in vacuum distillation, since you're creating a vacuum, you're reducing. So boiling point is the pressure at which the vapor pressure is equal to the atmospheric pressure, right?
Got it. Okay.
So if you create this vacuum, you will lower the vapor pressure, which means you're going to subsequently lower the boiling point of that thing. So it's used for things that have really, really high boiling points that are not practical for us to, reach. So that's yeah, so good. So yeah, that's how I want you to think about it. So like distillation takes advantage of the differences in boiling points. Um and vacuum distillation can be particularly useful for things that have really, really high boiling points because you can lower the boiling point by reducing the vapor pressure by creating a vacuum. And then chromatography, what's that? Like,
You just take advantage of like the fact that certain molecules are polar and others are non-polar, and there's like at least like seven different chromatographies that you could do.
yeah, there's also
But
70 different ways to see if something's polar or non-polar. So what does it
Mhm.
take advantage of, really?
Like there's two, I mean I know there's two like
Phases.
phases, yeah. So there's like the polar and the non-polar, but it varies which one is like mobile versus stationary phase.
So it's that, right? It's difference in affinities for the stationary phase compared to the mobile phase.
Got it. Okay.
So if you had affinity chromatography, you're not going to have polarity be a factor there. So
True.
so chromatography is defined as well, every single separation technique you want to think of as what what difference if I'm trying to separate things, what is different between the things I'm trying to separate that I could take advantage of. So for chromatography, it's yeah, different affinities for the stationary phase relative to the mobile phase. And that can include like size exclusion, right? That doesn't have to do with polarity. So it's not going to always be related like dependent on polarity is what I'm trying to say.
Mhm.
Okay. And what about you mentioned another one, another separation technique. What is it?
No idea.
Extraction.
Oh, yeah. I mean that's also like polar, non-polar. Okay, well, yeah, there's like two solvents.
Like
Um,
I think the easiest way to differentiate polar from nonpolar is taking it and putting it in water, seeing if it.
yeah, yeah, yeah.
So it's not like, all right, I need to go out to the lab to see if the water I'm drinking is. So it takes advantage of the differences in solubility between two layers. And yeah, you could have largely an aqueous layer and a organic layer. So out of all the different separation techniques, your thing of polar versus nonpolar is the most relevant for this one, I'll say, yeah. But yeah, you're taking advantage of the different solubilities. Good. Okay. So, um, okay, so yeah, we have our figure here.
Hold on, one more question. What exactly is the point of crystallization and like recrystallization? That's like the one I know the least about.
Oh yeah. So like so a crystal, aka a solid, can form if it forms really quickly, there will be impurities within it that mess with the crystalline structure, the highly, rigid crystalline structure of a solid, aka a crystal. So recrystallization involves you like not dissolving it, but you are kind of turning it into like a liquid again, and then you turn it into a solid again very slowly, so that the solid bonds can form in the in a more perfect configuration that does not have impurities locked or stuck within it.
I guess that kind of makes sense. So yeah.
Yeah, let me get a here in the chat. Solution lamp, it's impure. Well, I guess this is technically crystallization. Recrystallization is gonna be starting with the crystal and then doing this again. So yeah, the idea is that there's an impure solid that's in that in this case a solution, um, and that we heat it to evaporate. Well, I guess I didn't say this part. To evaporate most of the solvent, so you're left with the solutes, and then you just let it cool down really, really slowly for it to form more pure crystals rather than impure uh, crystals. And so recrystallization is pretty much the same thing, except you start with the solid. So you would have to then dissolve it in this solvent, and then do exactly what the rest of this is saying.
Mhm.
Mhm. So that's what that would be.
Wait, but so here, like, what's with recrystallization? I kind of it's a little more intuitive, I feel like. I mean, like you're just remaking the compound just slower.
Uh-huh.
This is like why you so you're evaporating the solvent,
Hmm.
but that I don't get step three.
Yeah, here. Let me consult my notes here. So recrystallization. Oh, that's actually okay. Separate solids from solids. So crystallization, you're starting with so if you just so for recrystallization, it's just like before this. You start with an impure solid, and then what you do is you dissolve the impure solid in a small amount of hot solvent, and this allows both the compound and the impurities to dissolve.
Mhm.
That's step one. Step two, you allow it to slowly cool, and that means that a crystal lattice will form spontaneously using like molecules, those of the compound, rather than unlike molecules, those of the impurities. Three, step three, when the crystals have finished forming, you can use filtration to separate the solid crystals of the compound from the liquid impurities. The liquid is called the mother liquor.
Okay.
Uh, key is to cool slowly so that the impurities don't get a chance to get added to the crystal lattice. You also want to use a small amount of solvent so that you get your crystallization, which is uh the opposite, like precipitation, which is like the opposite of dissolution. Because you don't want it to be, you want to get it as a crystal, like, and you can't have it mixed in a liquid, so that's why they dry it. And can be repeated to increase the purity, but at the expense of yield. So so that's pretty much the idea there. You have an impure crystal and you dissolve it in a solvent to separate the molecules that compose the crystal and the molecules that compose the impurities. And you slowly cool it so that it can form that crystal again, but with fewer of those impurities being embedded in that crystal.
Okay, got it.
Mhm.
Got it. So, okay, yeah, this is a, we discussed this. Okay,
Mhm.
next is NMR. Um, I
Yep.
will say NMR and IR seem to be sneakily making their way throughout this volume two section bank. So, especially IR, NMR and IR, especially IR.
Yeah.
So I'm gonna make sure to
Uh-huh.
memorize all the values.
Yeah. I mean, but we've kind of seen NMR and IR a lot in stuff. Um,
I haven't seen NMR yet on like, I mean, I've only taken two like recently, AMCs, but
yeah. Because a lot of that other stuff in the section bank volume two, I'm like, just like I don't know, like I'm where you're at in terms of like what. I still have to review that colony forming units problem, but okay, let's just see. So appearance of the methyl group protons in the HNMR spectrum of R compound. So I didn't even really look at this. So okay, figure
okay.
synthesis and kinetic resolution to form this. Okay, so we have this, whatever. We add this, looks like an anhydride. Um, and pyridine. Did you say something about a pyridine being a base?
Is it a base? I thought it was.
Um, yeah, because any like an amine is like basic, and I'm pretty sure a pyridine is, you know, a benzene with a nitrogen in it. So uh I guess I guess it could be basic because it's a type of amine. But okay, we have that, and then we add, seems like this does some nucleophilic attack, like this, binds to it, and then breaks this off, right? Oh wait, yeah, right. That seems like.
Yep.
Then we get this rad compound 3, and then we add Cal B, which is that Candida antarctica.
Hmm.
I wonder why it's called that part, but I'm pretty sure Candida is like thrush or something. It's like a STD type of thing.
Hmm.
But it, what did it do again? It like, it converts. Okay, whatever. But compound 3 and I guess compound. All right, pH room 7, room temperature, compound 1, and then compound 2. They have the same EE. Wait, oh, both of them high percent enantiomeric excess of greater than 93%. Yeah, they'd also throw like these like very like weird new terms at us, but they have the same EE percent. But it seems like there's a 14% for the compound 1 and a 30% for the compound 2. But all right, let's see. NMR, compound one is over here.
But it's so what I was confused about is it asks R compound one, and so what like I know it's this, but like they're not showing the figure of it, so I guess we have to infer, like which one it is, and so I'm guessing it's the R version of this or what?
Well, yeah, it says compound 1, right?
Yeah, so, but I'm just like,
Hmm.
because the thing is, it's being converted to different things. So, yeah, I mean, I guess it's
Oh,
still,
wait.
y y-
Uh, okay. Hold on. So I think what they're doing here, I think this entire thing is just so we can separate. So okay. What is a rack? What do you think the rack means?
racemic.
Yep. So we have a racemic mixture, which means that there's two enantiomers of compound one, right?
Got
And it seems like this entire thing is just so we can separate them, the
it.
enantiomers.
Okay.
Um, and this would really involve like a wedge kind of.
Got it.
But okay,
Okay, that makes more sense.
yep. What's the appearance of the methyl group? Uh,
Yeah, it makes sense now. I get it right now that
oh, because it has, so this is the methyl group and it has
yeah.
one hydrogen neighbor.
Yeah, so H plus one. Yeah, it's double it. Got it. Okay. Yeah, that makes way more sense because I, for some reason, was looking at rack compound three.
Yeah.
Um,
So, yeah,
okay. Um, let's say I asked for the H&MR of like this methyl. Would it be one?
it'll
Because
be
there's no hydrogens next to it.
correct.
So one, singlet.
Yeah,
Okay,
yeah.
got
Meaning
it.
n is zero and n plus one singlet.
Yeah,
Yeah,
okay. What is the role of pyridine in step one of figure one? Okay. Um,
you were saying. Oh,
yeah.
no, that makes perfect sense because it has the lone pair.
So, I mean, here they don't really tell us, like, I mean, yeah, I guess they do tell us the formula, but they don't show the structure of it.
Is this a,
What?
is this the formula for Pyrodine?
Um, if I was doing this, I would think yes. I don't know what it look. Actually, wait, I do know what it looks like.
You know what it looks like.
I know what it looks like, actually.
Yeah. And you knew it was a base because of something that it has, right?
Yeah, yeah, yeah. So
Uh-huh.
one, two, three, four, five. Wait, it might be like one, two, three, four, five. Well, it's supposed to be like this, I think. Like it's six total. Like heterocyclic ring with,
Well,
yeah.
really,
The main thing is this, yes.
it has a nitrogen and this does not.
Yeah. Okay, got it. So,
This is
okay,
the ether. The
got it.
what do they say?
Diethyl ether, yeah.
It looks like that, like a bird almost.
Yeah, yeah, like a bird. Got it, I got it. Okay. So, yeah, it is, well, okay, nitrogen with the lone pair. Um, I mean, trying to think here. Like, let's see. Honestly, I'm a little confused because, like, what exactly is it gonna do here? Um,
Well,
like the, oh,
remember,
it's gonna, yeah.
so remember how you knew Pyridine was so when you first started reading this, you knew Pyridine was gonna be basic,
Hmm.
and I thought you knew that it was gonna be basic because it had something in it, but how did you know it was gonna be basic?
So I just actually had like an Anki card that literally said Pyridine is a weak base. That's it.
Okay. So now
Like, yeah.
about what that can mean, right? So you know that uh a Bronson Lowry base um okay. So I guess I was thinking more so along the lines of a Lewis base because I was going to say
That's what I was thinking as well, like just now. Like,
yeah.
but yeah, it's not an answer.
I was going to say that because I thought it was going to have a lone pair.
Hmm.
But I think for uh the pyridine, I'm forgetting that it's it's like benzene. It has like uh
Yes, yes.
that, right? So that means that 1, 2, 3, like it shouldn't have those excess. Um, 1, 2, 3. Well, I guess it could have. But anyway, um, yeah. Oh, damn it, it has a radius base too. Well, that one, you know, that one's like if it makes OH minus, right? So, okay, so let's see what happens here. They said that compound 1 is converted to compound 3, adding 2 pyridines and 1.5 amounts of compound 2, which is the anhydride in the ether. Um, okay. Yeah. Oops. Does this. And then this thing comes out as that. The anhydride comes out as this. Or the H from this. I think that's what happens. Because when you make this bond, you're going to get like this attached to that. Oh, minus.
Wait, what?
So
Oh, yeah, yeah, okay. Yeah, yeah,
if this OH group attacks this carbonyl carbon over here,
yeah.
it will look like this first, right? And then like that will close that up, and then this will close that, so we can reform that double bond. Now, this OH is gone here.
Okay, what I was thinking is that the pyridine takes off the H.
Yep.
Okay,
Yeah.
yeah.
Yeah. Because compound 2, which is an anhydride, is going to be more acidic than basic. And the ether is not going to do anything. It's not polar. Um, so the pyridine is doing something. And so we know that the OH in compound 1 will nucleophilically attack the carbonyl of compound 2. And then, this will come back and then this will break off. However, we still have this hydrogen that we don't have over here. So it will be acting as a Bronson-Lowry base by accepting protons.
Oh,
Mhm.
interesting. Okay.
Yeah. If they had a choice that's a Lewis base, I probably would have chosen that because I was thinking, yeah, from the hydroxyl group, there we go. That reacts with the acetic anhydride, thus acting as a proton acceptor.
Hmm.
And like you should be able to see like this and know that this, attacks that, right?
Hmm.
Part of what I always say about if you see a hydroxyl group, think nucleophile. If you see a carbonyl group, think electrophile.
Yeah. Yeah, they give questions about polylinkers and then they give questions about this. Like, what is temperature in Celsius? Okay. Next is this. Um, yeah, so I'm pretty sure this is tertiary.
Yep, this is something you were.
Okay. Yep, yep. Just making sure. Okay, I got it right. All right. Yeah, this I got wrong. I know that.
All right. Of step 2 in figure 1. Step 2, like that's where I was like, okay, like they have the same EE enantiomeric excess, but R is like 14% something, S is 30% something. Um, so like, and they're telling us this is an enantioselective conversion, um, which would mean that it's a way for them to, because racemic implies 50-50, right? Half.
Yeah.
So doing something enantioselective is going to make it so that, you choose one or over the other. So you should have an unequal amount. Um, and I don't know honestly what this percent EE thing is, but I do see R 14%, S 30%. So that I would lead me to say that it is selective because it is selecting for the S enantiomer, right?
Mhm.
So, I mean, I guess that can narrow it down to D, but I haven't looked at the other parts. But low EE of compound one, they have the same EE percentage, so it can't just be low for one, like compound one, or our version of compound one. Stereoselectivity, non-selective, reflected in the low EE of the compound three. That's also going to be wrong for the same reason A is wrong. We have the same percent EE for both of these guys. Yeah. So okay, yeah. So that's just saying that there's. Oh, I guess this is also like even the second, like the first part, like 'cause at first I was looking at the first part, but also the second part. This is the only one that says high percent EE for both compounds, right? Which is true here. So even if we didn't know, like if this was selective or not, this is the only choice that says that both of these have high EE percent.
Got it.
Yeah.
Okay. I mean, yeah, we won't have time for another one, so that's it for today. And then, um, so tomorrow then we agreed on like around 4:40, right?
Um, Oh, that was okay. Yeah, I see 4:45 to 5:40 and then 6 to 7.
Yeah, yeah,
That's right? Okay.
yeah.
All right. Awesome.
Let me know how much was today.
Oh yeah. Let's see. 63.
Okay. And yeah, try to let me know whenever about that problem at the beginning because that was rough.
Yeah, yeah, yeah. I already have an idea of that.
Okay.
N is going to be the number of photoelectrons. E is the elementary charge. Yeah, I'll write it down.
Okay. 63, right?
Um, yeah, 63, yeah.
Yes. Okay.
All
I'll
right.
see you tomorrow.